So I recorded this lesson yesterday when I taught it to B-Day, and I know A-Day, you just had the notes the other day. And then both times I recorded it in 6th and 7th period, my iPad crashed right afterwards and didn't save the video. So there is not a video for this yet, and I'm not going to go through the notes like doing them. We're just going to look at it and make sure we understand what's happening. So in class on Friday, you were looking at the video of the conic sections. It doesn't matter where you drew these planes, as long as the first plane is flat, the second plane is slanted, the third plane, the hyperbola, is parallel to the axis of rotation, and the parabola doesn't go through the cone in both sides. That creates each of the conic sections. Does that make sense how that works? Did y'all watch that video? Okay. So this is why a parabola is what the shape of a quadratic is. A parabola is not a quadratic. A parabola is a shape that a quadratic makes, and it comes from this conic section, which I think is pretty interesting. Then very quickly, there was a review of circles. This is from section 2.8, so you have more notes over this if you wanted it. Does that all check out for you? Radius and center? Okay, cool. Then we started talking about the ellipse itself, and we have all of this vocabulary for the ellipse, your foci, which that's how you pronounce that, foci. It's the plural version of the word focus. You have your center, you have your major axis that should go through, apologies if this is not straight, that should go through the major vertices, the focus, and the center. So that's 5 points that end up on that major axis. The minor axis and minor vertices, and I'm using air quotes that you can maybe look at me doing because your textbook does not define them that way. I just know for hand graphing that it's very important to have your minor axis and your minor vertices as well. Then we had all these formulas. Did you notice that as tempting as it is, this is not Pythagorean theorem? Yeah. So when we're using this for an ellipse, don't let yourself accidentally write down Pythagorean theorem, which is a squared plus b squared equals c squared. This is minus a squared minus b squared equals c squared, but solved for c. Are there any major questions just from this page? It was kind of just like information about the shape, yes? When we go to actually solving these guys and graphing them, question for you. How did I know the center was at 0, 0? The H and the X, Y are by themselves, yes? As opposed to when it looks maybe like the third one. What is next to X and Y here? You see X minus 1 and you see Y plus 2. So the center is at the opposite signs of 1 and negative 2. So your center is always the first thing you want to find because everything is based off the center of the ellipse. One thing I want to make sure we understand here is that the larger value in the denominator is always a. So since the larger number in this problem was underneath the x, that means that the x is going to be longer. So you have a wider ellipse as opposed to a taller ellipse. In the second example, the larger value, the a value, was underneath the y. So you're going to have a tall, because the y values go up and down. So it's going to be a tall ellipse as opposed to a wide ellipse. For after you found the a, b's, and c's, which is a and b from the equation, c from the not Pythagorean theorem, you found these three coordinate points, the foci, the major, and the minor vertices. Do we understand the concept that I was trying to get you to do here? That each of these start with the center, 0, 0, 0, 0, 0, 0. But then you add and subtract a number, a, b, and c, either to the x value or the y value. To the y value or the x value, depending on if you have a wide or a tall ellipse. So you're always starting with the center and adding and subtracting a number to that. This is incredibly important, especially when the center is not at 0, 0, like in this third example. Did you see how every time I started with the center at 1, negative 2, 1, negative 2, 1, negative 2, but I added and subtracted a number either to the x's or the y's? That's the process you're doing each time. A question I assume that you might have if you started your homework already is that I'm calling all of these major and minor vertices, but your textbook and the first few problems of your homework are going to call them the x and the y intercepts. Why do you think specifically on like this first example, we can call the major and minor vertices x and y intercepts?
Because it's on a 2D plane.
Correct. It's on a 2D plane, and where's the center of these ellipses? So my major vertices are my x-intercepts. and my minor vertices are my y-intercept. Or in this one, my major vertices are the y-intercept, and the minor vertices are the x-intercept. They're going to change that language when you get to the further along in the questions and we start translating this off of the origin. Notice that the vertices are no longer x and y intercepts. The textbook's going to change how it refers to them. I'm just going to call them major and minor vertices the whole time because it makes more sense to me. Is that cool? Okay. I'm going through this fast because when we go over the hyperbola today, it's kind of going to be the same process, so you can go back and apply that thinking here as well. On this last page, what we did is we took information about the ellipse, which was that we had foci at -1 and 1 on the x-axis, and major vertices at -2 and 2 on the x-axis, and we were able to work backwards. If this is where the 4 points are, that means the 5th point, the center, has to be right in the middle of it, which means my center is at 0, 0. If my center is at 0, 0, the distance that the foci is from the center is c. It's called the focal length. So c is 1. The major vertices are given by the a value. That's the distance from the center to the major vertices. So I know a was 2 and c was 1. All I had to do was solve for b using the not Pythagorean theorem. Did anybody notice my typo on this question, by the way? What is the square root of 3 squared?
3.
It should just be 3. My bad. I noticed that like halfway through the day and I was like, too late. That should just be 3. Square root of 3 squared is 3, not square root of 3. My bad. And then last but not least, we took the general form of an ellipse, like the general form of a circle, and we completed the square twice to be able to write it in standard form. Let's walk back through these steps now that you don't have to hurry up and write along with me. You're just looking with me. What did I do this first step? Here. I made my boxes. So I grouped everything. Here's all of the x's and the box for x. Here's all of the y things and a box for y. I know it's a circle. You get it. And I moved the 532 to the other side. It became negative, but I made sure I added the mystery box numbers to that side as well. Do we understand?
Yes.
Okay, here's what might have been different. And because I couldn't explain this out loud to you, you might be like, why did we do this step? Remember when we were completing the square back in chapter 1? And in chapter 1, we said we can only complete the square when the value in front of x squared or y squared is 1. So what would I have to divide this by to make this 1? 4. So I have to divide all of the x's by 4. And I can't just let it go away like I did in chapter 1 because we did that in chapter 1 since the equation was equal to 0. And 0 divided by 4 would still be 0. So we could basically just let the 4 go away. We can't do that here. So we put the 4 in front of a set of parentheses. 4 divided by 4 is 1. 40 divided by 4 is 10. Check?
Yeah.
But here's the deal. Since you have this 4 in front of this box, it's as if we would distribute the 4 to the box as well. So when I go write it on the other side, what do I have to put in front of that box?
A 4.
A 4. We repeat those steps for the y's. What do I need to divide this y squared by? 36. So I take out the 36. Negative 228 divided by 36 is negative 8. That's nice. Not a fraction. But since I am multiplying all of these terms by 36, I have to go multiply the other mystery box number by 36. Do we see that?
Yeah.
Okay, great. This looks horrible, right? Yikes. But now we can complete the square. We do b divided by 2 squared. 25 is the mystery box number. We do b divided by 2 squared. 16 is a mystery box number. So I put 25 and 16 in all of the boxes. 4 times 25 is 100. 36 times 16 is 576. So negative 532 plus 100 plus 576 is 144. Just added all those things together. Since I showed my work in completing the square, we know the 5 drops down and we know the negative 4 drops down. Let me answer this phone first. Once we have the completing the square written, remember we showed our work so we know what number drops down into the perfect square trinomial. So this factors to x plus 5 squared and this one factors to y minus 4 squared. Y'all read my note, I'm sure. Yeah. So since this should be a 1, ellipses are always equal to 1. What do we have to divide everything by?
120.
144. 4 over 144 is 1 over 36. 36 over 144 is 1 over 4. And 144 over 144 is 1. So in doing this, I now have a standard form ellipse that I could tell you all the information about. The center is at -5, 4. The A value is 6. The B value is 2. I could use the not Pythagorean theorem to find C, and then find the coordinates of the foci, the major vertices, the minor vertices, and graph the function. That was fast and furious, I know it, but when we go over the hyperbola today for our actual lesson, you're going to see that these concepts repeat each other, that we're going to see the same sort of layout, and so if you still have questions in the ellipse, I might answer it in the hyperbola lesson. Cool? All right.